Welcome into our next video. And just so you guys know, I know we are moving fast. Hopefully no one's too stressed out, but the first 2 weeks, they go by quickly, especially with all these topics. Again, we're stealing all of this from the end of Calc 2 before we jump into Calc 3. I promise as soon as we get into Calc 3, which is in week 3, we'll slow down a little bit. We'll be able to take a deep breath. But these first 2 weeks, very hectic. I know. Please feel free to ask for questions, for help. Come to my office hours, and obviously come to class with questions. Right? But I do know these first videos here on sequences, series, parametric equations, polar equations, it's a lot to cram into 2 weeks. It's very condensed, very fast. So do your best to stay on top of stuff. Again, ask as many questions as possible. Once we make it to week 3, we get to take a deep breath. Right? But until then, we got to keep going here. Right? So today, what we're going to talk about, or what we're going to introduce, are series. Again, normally we would see this at the end of a Calc 2 if we had 3 semesters of calculus. Now, before we get to series, I want to make sure we remember what we were dealing with before, which are sequences. Right? And we were denoting sequences with this A sub n, right? We were using this as the sequence. And all we're going to do with series, in particular infinite series, so let's put this, normally the infinite would go before, is we're going to take all of the terms of our sequence. So we're going to add up all, right, infinite terms of our terms in our sequence. Terms in our, and I'll move out of the way, sequence. All right, so that is the idea. All right, we're going to take all of the terms in our sequence and we're going to add them up. And eventually what we're going to get to, we're going to progress to this, is we're going to see whether or not we converge to a particular value or if we diverge, right? So just so we have the notation down, this is what it looks like. We're going to say the series, and if it's an infinite series, is going to be equal to sigma, right? So let's not be afraid of math notation here. This sigma here just means the sum of, right? So sum, it's just a giant summation. Sum from n equals 1, and it doesn't always have to start at 1, just so we know. It can start at many different values, a positive integer, to infinity, right? So of our sequence A sub n. So the idea here is we built upon what a sequence is. We have this infinite list with all of our different, right, terms of our sequence in it. And now we want to know if we add up all of these values, right, will we actually come up to a defined, right, sum, right? It'll actually be some value, or will it just keep going on forever and ever and diverge, right? That's what it means to diverge. There's no actual value that we will sum up to or get close to summing up to, right? So this is the idea. So what we start with is we go, okay, we want to introduce series, right? But let's get an introduction by starting off with easier ideas known as partial sums, right? So before we address the idea of adding up to infinity, we start off with a little bit of an easier idea known as partial sums. Right, infinity, right, very scary, but this idea of partial sums, right, is going to say, well, maybe if I have, right, some sequence, A sub n, maybe I just want to add up the first 5 terms. Right, so just getting used to adding up terms here, right, so this would be S sub 5. Right, we put a 5 here to denote that we just want to add up the first 5 terms, and what this looks like is, right, you would take A1, add it to A2, add it to A3, A4, and A5. And of course, to get these terms in the sequence, we might have to do some calculation also to be able to find what they are. Right, but this is the idea of partial sums, right? And eventually we're going to tie these two ideas together, partial sums and series, right? How they interchange or interconnect, let's say. But for right now, we just want to get used to the idea of partial sums. Right, so series, right, we're going to be dealing with infinite series built on top of the foundation of sequences, which we already touched, right? And we're just adding up all the terms. So again, all that's happening here, this summation is just say adding up, or summation, right? Sum. And you can see that's identified here with all of our plus signs. So let's start with one example. I only want to do one example of this because I'm sure this is very similar to the same way that we did sequences, right? It's kind of a little bit tedious. We have to go find it and then add it, find it, then add it. So we're just going to go through one example here. So let's say, and I'm not going to do 5, let's say, I'll draw a little bit of a line here. I'll say find first 3. So I want the first 3 partial sums. And I'll give you some series here. So let's go ahead, we're going to do the series. We'll say the summation from n is equal to 2, right? So notice that it doesn't have to start at n is equal to 1 to infinity. And I have 5n over n plus 4, right? This is my sequence. Okay? So what I need us to solve for is s sub 1, right? What is this equal to? Or in this case, right, it's s sub 1 because we're only doing one term, but I'm going to start it at 2, right? Because it starts at n is equal to 2, so I'm just going to write this as 2. This might be incorrect notation, but just so it makes a little bit more sense, we'll put a 2 here, meaning I'm only going to plug the 2 in. Now, if I do s sub 3, that means I need to add s2 plus s3, or s2 to whatever we get here. So let's go through an example before I confuse anybody. So we're just going to do s2, right? Meaning I'm only going to take my very first term here and plug it in. All right, so this is going to be 5 times 2, and we'll shortcut this part, over 2 plus 4, going to be 6, right? So when we plug in just our first value, all we end up getting here, right? So let's put 10 over 6, which is 5 over 3, right? So this is really just equal to a sub 2. Since it's the first one, it's just equal to the very first term in our sequence, right? This is the very first term in our sequence because we're plugging in 2 to start. And since it's the very first one, right, there's nothing to add it to, so that's all it is. Now, when it comes time to do S3, right, all we're going to do is we're going to do A2 plus A3. Right, I'm using A sub n, just in case I've lost anybody. I'm using A sub n, right, because this is our sequence, as a shorthand notation. Right, so S sub 2 in this case is just the first term, A sub 2. Right, so I plug in 2, 5 times 2, I get my 10, 2 plus 4, I get my 6. I make this simplification, right? And since it's my first term, I have nothing else to add it to, right? So there's nothing to sum up. Once I get to S3, right, the partial sum, right, with n is equal to 3, now I have to add A2 plus A3. But the good news is I already have A2, right? So all I need to do is calculate really what A3 is. So this ends up equaling, right, A2, which is 5/3, plus, now I do need to go calculate what A3 is, right? What is A3? Well, if I plug in 3 here, what do I get? 5 times 3, 15, divided by 3 plus 4, 7. And I'll pause for a second while you're copying that down. But what are we going to have to do here is find a common denominator, right? Unfortunately, it's the ugly 21. So we go 5/3 and we need to change it to the common denominator of 21. We multiply the top and bottom by, correct, 7. we'll do one more example quick with partial sums, right? If you already felt really comfortable with example 1, speed on ahead. Totally fine. Okay, so we're going to do the same thing. Find first 3. I know your homework has 5, but for time's sake, I'm only going to do 3. Partial sums of, let's do the series, right? The infinite series. So this is the sum. We'll start at 1 this time, so I don't mess up any syntax here. 1 to infinity. And let's go ahead and we'll do, we'll do n plus 1 squared, and we'll do, let's do n factorial. Just to make it different, get used to factorials, get used to squaring, right? We just want to do the first 3, right? So the very first one we want to find here is S1, right? Well, S1, and just so we remember, right, this is our sequence, right? We're adding up all the terms of our sequence. So if you ever see me use this as shorthand, A sub n, I'm referring to our sequence here. Right, I'm referring to the sequence. So for our very first one, right, well, let's just write out what it is. In this case, this is just going to be the sum of, well, our first term, right? So it ends up just being A1, right? So I need to just plug in 1 here, and what do I get? Well, I'll write it all out. I get 1 plus 1 squared all over 1 factorial, which is going to be equal to 2 squared, 4 over 1, so 4. Right, so again, this should seem familiar from when we did sequences, right? When we were doing sequences, same steps, sorry about that. Same steps we were doing, the only difference is now we're going to just start adding things together. Right, so for S2, let's say, S2, this is just going to be A1 plus A2, right? That's what it means by the sum of, right? This is the sum, this would be the series, the sum. So I take my first term, I add it to my second one. Well, I already found, right, my first one, it's right here, 4. So 4 plus A2 is equal to 4 plus, well, what happens when I plug in 2, right, into our sequence? I get 2 plus 1 cubed, squared, all over 2 factorial. And this ends up being 4 plus 3 squared, 9 over 2. And then we start dealing with fractions, which is always fun, so we have to deal with some algebra, right? We just need to get a common denominator here of 2. So we have 8 over 2 plus 9 over 2. And that gives us 17 over 2. Right, and again, this is the sum of A1 plus A2 for our partial sum. Okay, and we'll do our last one over here. We'll draw a line. We want S3, which we know is going to be A1 plus A2 plus A3. Right, you could also think of this, just so we see the summation notation here. This is the sum from, let's do n, we did n, equals 1 to 3, right, of this. That's exactly the same thing. I'm just writing it the other way. Okay, so again, same thing. We're just taking our first term in our sequence, adding it to our second one, adding it to our third one. The good news is, what do we already have? Well, I did this from our previous, right, partial sum, A1 plus A2, which we know to be 17 over 2. So part of our work is already done. And now I just need to add A3. Well, what is A3 going to be? So 17 over 2 plus, we plug in the 3, 3 plus 1, 4 squared, 16 all over 3 factorial, right? 3 times 2 times 1, 6. So, right, this is going to be 17 over 2 plus 8 over 3, and what's a common thing that we've been doing here? is finding a common denominator. We have to multiply 17 over 2 by 3. Which means we have to multiply this one by 2. So finally, after everything's said and done, right, our third partial sum, 67 over 6. All right, so that was it. Quick example for another partial sum. Feel like 2 examples is good. I will see you in the next part of this video. We will start to go over is if we have a series and we want to know whether it converges or diverges, what steps do we take to solve that process? So we will get into that soon. All right, hopefully you paused the video at some point, taking a break. I know I make these a little bit longer than I initially said. They're about 30 minutes, so no worries if you gotta watch them in pieces. Okay, so back to the real meat of what this section is about. Right, series. Now we've talked about partial sums. Right, and again, eventually we're gonna introduce that a little bit further along the road. But the real key here with series is that when it's given to you, right, so you have some summation, some series here, it's going to be, will be an infinite series. Let's just say it starts at 1 for right now, to infinity, of a sub n, right? This is just some arbitrary series. The real key that we have to do here, right, is identifying what type of series is this by identifying what type of sequence is this. Right, this is the key. We need to identify this. So think of the process as being, eventually I want to know, does this series, so we'll just say does series, and I'll move out of the way here, it's a weird S, series diverge or converge, right? This is the question that we're asking ourselves. Does this series diverge or converge? This is the question. Now, in order to answer this question, we first have to identify what type of series we're dealing with, right? After we have identified what type of series we're dealing with, then we can go through our toolbox. Now, I can imagine we're all asking, what does he mean by toolbox? We have no tools in it right now. So slowly, what we're going to do between this video and the ones coming are slowly build our series toolbox, right? By getting better and better at identifying the different types of series. So I'm going to go step by step breaking down the different types that we're going to encounter, starting with the geometric series. So the very first one we're going to talk about is the geometric series. All right, and I'm going to give an example. So let's do example here. So let's say we have the sum of, we'll do an easy one to start off with. We'll start with n is equal to 1 to infinity, and let's just do 1/2 to the k. 1/2 to the k. And what I want us to do is write out a couple of terms, right? Just so we get the idea. It might be obvious from this example, but just so we get the idea, what happens when I plug in 1, right? I get 1/2, right? 1/2 to the first power, I get 1/2. What happens if I plug in 2? Well, I have 1/2 squared, so I get 1/4, right? So this is the beginning if I started adding up all these values. Let's plug in one more, right? 1/2 to the third, 1/8. Okay, plus dot, dot, dot. It keeps going. Right, so the question is, how am I getting from 1/2 to 1/4, from 1/4 to 1/8? Is there some sort of pattern? Well, we know there to be a pattern because I gave us an easy sequence here. What are we doing each time? Well, I'm just multiplying by 1/2, right? From here to here, from here to here. I'm multiplying by 1/2. So when we have this pattern where we can see that every time we move to our next term, right, we're just getting it from multiplying by a value to get to the next one, right? This is what's called the common ratio. So I'll put a bracket around this one, right, the 1/2. Right, this is known as the common ratio. right? Every single time I'm multiplying by the same value to get the next term, right, in my sequence. In this case, we're adding it so it's a series, right? In this case, it's pretty easy to identify because that's the only thing that's here, right? 1/2 raised to the k, every time I add a new term, I'm multiplying by another 1/2, right? 1/2 to the first, 1/2 squared, 1/2 cubed, etc. Right, so we have a very specific rule when it comes to geometric series. What we know is if r, so here's, let's make a rule here. Right, and we'll make a rule. So let's say, we want to know when does this converge? Right, we want a rule. When does the geometric series converge? And the rule is here, if r is between 1 and -1. Notice that they're not included, right? Between 1 and -1. And so the question is, well, why is that true? Well, let's look at just the summation that we've written here. I started off with adding 1/2, then I added 1/4, so I keep adding smaller and smaller values, right? What's next? Over here is 1/16. Then it's 1/32. So I keep adding smaller and smaller values. So the idea is, eventually, what is this going to get closer and closer to? It'll get closer and closer to 0, right? 1/64, 1/28, 1/256, 1/5/512. It'll keep getting closer and closer to that 0 mark. So eventually it's going to feel like I'm adding nothing, right? So I know it's going to converge if my common ratio is between -1 and +1, because any value between there, the more times you multiply it by itself, it's going to eventually converge to 0, right? Even if I chose 9/10, if I keep doing 9/10 to the millionth power, right, eventually it's going to get arbitrarily close to 0, right? So if we are between -1 and 1, we converge. And we're going to put a star by this because we need to talk more about this. All right, so first thing is identifying, does it converge, does it diverge? And so you could guess, right, it diverges if, let's say, the absolute value here, I'll rewrite it this way, you could have used absolute values here, is greater than 1. Greater than or equal, I think we want the equals, I'm going to double check on that, equal to 1. Right, it's going to diverge. So, right, if we're between these two values, right, we converge. If we're outside of those values, we diverge. But the key thing is we have to be able to identify r, which is the common ratio, right? So just in case I didn't write this, the common ratio we denote using a lowercase r, right? This is our common ratio. Okay. So it all comes down to just finding out what r is. Now, if the first thing is, again, identifying, converge or diverge. Once we have that, if it converges, right? So if it converges, I actually can calculate what it will converge to, right? Well, how do I do that? It's not that bad of a calculation. Where did I write? It's going to be, our sum is going to be equal to A1. So this is the very first term in our sequence. Very first term. So we need to be careful because if I switch this number, right, I need to double check what my first term is. So A1 over 1 minus R. A1 over 1 minus R. So in this case, let's figure out what it is. So in this case, what is my very first term? Well, if I plug in 1 here, I get 1/2 over 1 minus my common ratio, which is 1/2. Well, what does this end up being? This is actually a very nice one, right? 1/2 over 1/2, which will just be equal to 1. Right, so our sum will converge to 1. And that makes sense, right? We have 1/2, and we have half of what's left over to get to 1, half of what's left over to get to 1, and so forth, right? So we never actually reach 1, but we approach 1. Right, so that's what the sum will actually converge to if we just kept going for infinitesimally many terms here, right? So this is our first example, right? It all comes down to first finding the common ratio, identifying whether it converges or diverges, and then we can easily find, right, the sum if we need to. So again, right, we're slowly adding to our toolbox here. Our very first one is geometric series. I'll do a couple more examples and we will call it a day. So I'll see you here shortly. Take a break, stretch it out. I know it's a lot. See you guys. We're going to do two quick examples as far as the geometric series. So again, these are related to the geometric series. So we want to get comfortable with the geometric series before we start adding in more, right, stuff into our toolbox with other types of series that we're going to run into. So again, geometric series, what are we looking for? The common ratio, right? Does it have a common ratio? That's our question. So let's do one that's slightly different. Another example here. So let's say I have a sequence, and we'll say from n is equal to 1, not sequence, series. N is equal to 1 to infinity. We have 2, and I'll do times 3 to the n minus 1. And again, what helps here is to write out a few, right, of these sequence terms, right, and see what's happening. Now, what I'll mention here is, let's just do this. Our very first one, we're going to plug in 1. All right, so I have 2 times, and maybe you have already caught what I'm about to do. 2 times, if I plug in 1 here, this is 3 raised to the 0, which is going to be 1, plus 2 times, if I plug in 2 now, I have 3 raised to the first power, plus, we'll do one more, 2 times 3 squared, right? So what is happening here? This essentially, right, is 3 raised to the 0. Right, so each time, what am I multiplying by? I'm multiplying by 3. So we do have a common ratio, right? What do we also notice? You'd put plus dot dot dot. What do we also notice? That each time we're multiplying by 2. So the question is, do we really need to do this with every term? No, let's just pull it out to the outside, right? So we can simplify this. Right, so the 2 is on the outside. Now we can't forget about the 2. We are going to need it. But immediately, since we have a common ratio that we are multiplying by each time, we immediately know, okay, this is a geometric series, right? So let's go ahead and see, right, whether it converges or diverges. Well, what is my common ratio here? My common ratio is what? Well, it's 3, right? And then we need to recall our rule that we learned, right? We know that it will converge, so I'll write it over here. So we have it, it'll converge if R is between, let's just say R is between -1 and 1. And we look at our R and we go, well, that's not true, right? It's outside of those bounds. So then we know that it must diverge, right? Another way of writing this, the absolute value is greater than 1, right? So we know that it diverges. Okay? I'll see if I can fit one more example in here, kind of awkwardly block it off. Okay, so the one more example that we'll do looks more complicated than it is. Let's say we have another series, and again, I'm only giving you geometric, so it is helpful that we know ahead of time that it's going to be geometric. And this is k is equal to 1, so we're going to use k as the incrementer instead, not that it matters, to infinity, and we'll do x to the k all over 4 to the k plus 1. Right, and what this question goes on to say, I'll put it somewhere in the corner, right? What the question wants to know is, for what x values will I converge? For what x values will I converge? Right, so what this question is saying is here's this arbitrary geometric series. I want to know what x values can I plug into this and have my series still converge. That's the idea here. Well, in order to do this, right, what I want to do first is make a simplification here. Right, notice that the top is k and the bottom is k plus 1. So let's go ahead and rewrite this. Right, so I'm going to make sure everyone follows. This is to the infinity still, nothing's changed, k is equal to 1. And the way I'm going to rewrite this, and we'll stare at it for a second, is this is, right, I'll write it down here. 4 to the k plus 1 is equal to 4 to the k times 4, right? This is the side math that we need. And so what I'm going to do is I'm just going to lead with the 4 instead, right? 4 times 4 to the k. And so what I can do is this is just a 1/4 here. The same way in our previous problem I could bring the 2 out, I can just bring the 1/4 out and that's fine. All right, so let's go up here. All right, I'm going to bring this 1/4 out, and now I have my summation, k is equal to 1 to infinity, and we're going to say this is xk over 4 to the k. And now, right, last thing for algebra's sake, now we can get it in this geometric form where it makes life a little bit easier. We have x over 4 to the k. So even though we don't know what x is, we know what our common ratio is, because if you write out some terms here, what are we multiplying by each time? We'd be multiplying by an additional x over 4. Right? We'd be multiplying by an additional x over 4. So we know our common ratio here, so r is equal to x over 4. Right? This is our common ratio. Now the question is asking for what x values will I converge? Right? So in order to answer that question, we need to remember we will converge when our common ratio, or r here, right, is between -1 and 1. So if I know what r is equal to, I just need to make this substitution and say, well, okay, that must mean x over 4 has to be between these values. Right? All I did was switch. This is r is equal to x over 4. I made the substitution, and now I can solve for x. Right? Well, how do I do that? Is I multiply both sides here by 4, and I end up with -4 x and +4. So I know that I am going to converge on the interval from -4 to +4, right? This is where I know I will converge, right? And I'm going to pause at this part. I don't want to do the whole problem because this is straight from your homework. But the second part is going to ask you, well, if this is where I converge, what will I converge to? So think abstractly, right? Again, the solution for solving my sum, I'm going to give you the equation, is equal to a1 over 1 minus r. Right? This is how we find the summation. So imagine, right, I know what my r is. I can find out what my a1 is. Right? That's how we can go find the summation. So I did the first part for you. Go ahead and do the second part on your own. That is it for this video. I know this was a longer one. Again, the first 2 weeks, right, there's a lot of material, right? We're covering some stuff at the very end of Calc 2. As soon as we make it to week 3, things will slow down. So just let's make it through these first couple weeks. Ask as many questions as possible. Stay positive. We'll get through the first couple weeks. I will see you in class.